So yeah, welcome back to another week of revision. We're going to talk mainly about proofs today. So we'll work through starting off with algebraic proofs, then we'll do some vector proofs, and then depending on the time, I don't know if I'll get around to circle proofs today. Typically with those, it's asking you to prove the circle theorems. So I'm not going to get too much into that. I might speak about it a little bit, but we're going to focus on the algebraic proofs and vector proofs. Okay, so we're going to leave these two questions on the back burner for a few minutes. Excuse me. And we're going to talk about some of the terminology behind proofs. Okay, so let's go ahead. Let's start this off, and we'll talk about the terminology of proofs. Okay. So pretty much when we are talking about proofs, in order to prove something, so we want to prove something. Basically, what they're trying to say is that for any, and I guess again, for our intents and purposes, usually if we're talking about algebraic, as an example, for any number, the statement is true. Statement or expression will be true. Okay, so whatever it is you're trying to prove, that literally for any number, it could be 1, it could be a million, it could be -1, could be 0. We're trying to prove within those confines of the question, really, is what we're looking at. Okay, so that's what we mean when we're saying prove X, Y, and Z. So getting into some of the actual terms that you'll see quite often, let's go ahead and put a couple on here. So you might be asked to show any number. So any number we could show as maybe the variable n. Okay, so n is probably the most common variable when we use in proofs. Again, could be x, could be q, could be r, it doesn't really matter. If we look at any other number, we could use a letter like m. Okay, again, doesn't really matter as long as it's not n. So that's pretty straightforward. Now comes the good parts. If we're looking for an even number, so some sort of even number, what could this be represented by? Because this is the part where lots of students kind of struggle at first. How do we come up with an expression or a term that shows that we have an even number? What do we think? Need to hear from you guys in the chat. We're going to need a really active chat today. 2n, perfect. All right. So remember that an even number is any number that's divisible by 2. Okay. So if we have 2n, that guarantees that we're always going to have some sort of even value. Okay. Now, when we look at an odd number, this is where, this is really just according to your flavor. So if we're looking at some sort of odd number, we're going to have 2n plus 1. Okay. So in this case, we could also say 2n minus 1 or 2n plus 3. Those will also be odd numbers as well, as long as we understand that we have to add some sort of, or add or subtract some sort of odd number onto the 2n. Okay, so again, the reason why that's true is because this will be even, and then anything even plus an odd number, so even plus odd is equal to some sort of odd number. Okay, so hopefully you understand why that's going to work. Okay. Now, if we look at the terms consecutive, right? So consecutive numbers, we could have n plus 1, n plus 2, dot, dot, dot. We can apply the same thing to consecutive even numbers, which is just going to be 2n, 2n plus 1, 2n plus 2, and so on. And then we can extend that again to consecutive odd numbers, which is just going to be 2n plus 1, 2n plus 3, 2n plus 5, and so on. All right. The last thing that I want to talk about is the square of whatever. Okay, so let's say the square of consecutive numbers. or the squares rather. And I'll put this in blue because again, you might be asked for one square, you might be asked for multiple squares. So squares of consecutive numbers. This means that we're going to have, let's start off with an n. So this means that we're going to have n squared. We're going to have n plus 1 squared, n plus 2 squared, and so on. All right, so just understanding what they're asking for when we're looking at this type of terminology. Okay, are we all good with this terminology before we get started? I get some. Oh, sorry. Sorry, I missed. I meant to put +2 and then +4. Sorry about that. Thank you for catching that. +2, got a little ahead of myself. +2, +2, and then +4. Thank you for catching that. So +4. All right. So let's get back to those two starter questions. So we're going to look at being able to prove algebraically that the sum of any two consecutive integers is always an odd number. Okay, so starting off with some of the terminology here, let's go ahead and highlight some of those important things. So the sum of two consecutive integers is always some sort of odd number. Okay, so what we're going to do first is we want to come up with some sort of statement. Okay, and we want to be able to define what our integers are. So we can say let x and x plus 1 be two consecutive integers. And then we can say that if we're going to add them together, x plus 1, and that's just going to equal to 2x plus 1. And we can see here that 2 times some sort of number is going to be even, and even plus an odd number is going to be odd. Okay, therefore the sum of any two consecutive integers is always odd. All right, so that's a pretty quick one. That's probably the most basic type of proof that we can get. Again, this is just to make sure that we're comfortable with that terminology. Okay, so two consecutive integers, x plus 1, we're going to add them to, or the two of those together. We see that we have 2x plus 1. We know that 2 times a number, or 2 times any number, is always going to be even. And an even number plus 1, which is an odd number, will be an odd number. Okay. Coming down to the second one, we're now going to look at 3 consecutive even integers. Is always going to be a multiple of 6. So one of the things that you'll need to really get is how to factorize something. So how to factor it a GCF in this case. So let's say, excuse me, I've got a frog in my throat. Oh, excuse me. Okay, so we're looking at the sum of 3 consecutive even integers, and we're looking at a multiple of 6. Okay, so even before we get into this question, we want to understand what a multiple of 6 looks like. So a multiple of 6 means that I'm going to have 6 multiplied by something inside of the brackets. Okay, so that's what we're looking at. So we're going to say let 3 consecutive even integers be, let's go with 2n plus 2, 2n plus 4. And then from there, we're going to add them all up. So 2n plus 2n plus 2 plus 2n plus 4. And from here, we can see that we have 2n, 2n, and 2n gives us 6n. And 2 plus 4 gives us plus 6. So again, coming back up to this statement here, we want to try to factorize out a 6. Our GCF in this case is 6. So we look and we can see here that we have some sort of multiple of 6. Okay. Any questions regarding this particular answer here? No questions? So you can say n plus 1 is a multiple of 6. Okay. So let's look at some more difficult questions here. So I'm going to put a couple on the screen here that are going to be a little bit more involved. Okay. So let's go with something like this one. Oops. Pop this one onto the screen here. So this one, it says that n is an integer, and we want to be able to prove algebraically that the sum of n plus 2 times n plus 1 and n plus 2 is always a square number. So there's not a lot that's different, but it just looks different in terms of the question. So what is our first step going to be? What do we need to do first? Yeah, we can expand our brackets. Perfect. So we're going to expand those brackets. And even if you're not really sure what to do, we want to be able to understand what our end result is going to look like. Okay, so our end result, we're going to look for some square number. Okay, so I find it helpful for you to define what you're looking for as an answer. So if you're looking for something that's a square number, we're looking for something inside the brackets that will be squared. Okay, so if you don't end up getting this as your result, then you know you've done something wrong. So we're going to expand our brackets. So again, we can use FOIL, we can use the distributive property, whatever you want to use. Okay, I'll do it in red and green, feeling very festive. It'll be Christmas in how many months? 8 months. So we're getting close. Also, I'm not a big fan of Christmas, by the way, just in case anyone's wondering. Not my favorite holiday. N squared plus n plus 2n plus 2. I don't know if I'm the Grinch, but I just think that there's better holidays out there. Yeah, n squared plus n plus 2n plus 2. So we're going to add n plus 2 as well. Okay. Let's go ahead and do that. Oops. Where did my mouse go? Here you go. So then we're going to add this n plus 2. So let's collect all of our like terms. So n squared is on its own. Then we've got n, 2n, and n. So that gives me plus 4n. And then we're going to collect our constant terms. So that's going to be plus 4. And from here, we're going to see that we need some strong factoring skills. So n squared plus 4n plus 4 can actually be factored as n plus 2 times n plus 2. All right, so we're looking for two numbers that multiply to 4 and add up to 4. So it's going to be positive 2 and positive 2. And we can see that because we have the same factor here, it's like saying that we have 5 times 5. I can now rewrite this as n plus 2 squared. All right. So we've been able to show that the sum of this expansion plus n plus 2 is going to be some sort of square number. Okay. Okay. So let's do something a little bit trickier. So I'm going to ask you to do this one on your own. So this one might be a little bit trickier. I'll put a couple here on the screen. So I'm just kind of plucking these from random places. So again, the main sources that I use for extra practice questions are typically Maths Genie and excuse me, Maths Genie and Corbett Maths. Those are the two that I normally pluck questions from. And I'm hopefully I'm going to be able to give you guys some actual exam questions as well. So give this one a try. I'm going to put this up on the screen here. So give this one a try. And if you're done with that one, I'm going to put the second one up on the screen as well. So I'm going to give you guys a few minutes to work through these ones and see where we get up to. Oops. Sorry, that's not the one I wanted to give you guys. Let's go with these two. There we go. So prove that the sum of the squares of any two consecutive integers is always an odd number. And prove that the difference between the squares of any two consecutive integers is equal to the sum of these integers. So again, I stress that you should break down each of these questions into its component parts. So even if you don't score full marks from it, you can actually still score at least one or two. So that's kind of the goal, especially if you've been doing mocks and you're sitting around that 5, 6, 7 range. Okay. I'm not going to expect you guys to, well, I'm not expecting all of you guys to get them all right. Obviously, it would be ideal, but during a test, you're going to be stressed. And you don't, yes, you'll probably blank out, some of you guys, and that's perfectly fine. But how can you score, 1 mark, 2 marks rather than leaving this blank? So you're just going to look at the component parts of the question and see if you can figure out something that you can do to at least earn yourself at least 1 mark, maybe even 2 or 3. So take a few minutes, work through these ones on your own, and then we'll take a look. Okay, so I know that not everyone is 100% done yet. That's all right. But do you want to try to get through a few more examples and give you guys a chance to work on an exam question from a past paper? So the first one says that we want to be able to prove that the sum of any two consecutive integers is always an odd number. Okay, so what we want to do is I'm going to highlight some of these important portions first. So we are looking at the sum of the squares of any two consecutive integers, and we're looking for it to be some sort of odd number. Okay, so it's a little bit trickier to know what what our end result is going to be. All right, but again, because we know that some sort of odd number could look like 2n plus 1, the part that might look a little bit different is obviously this is just any odd number. And then we want to understand that this portion right here could look like anything. So it could be 2 times whatever, and then even minus 3. Okay, so that's what we have to understand when it's not quite as clear what it could look like. Okay, we just need to be able to kind of to understand what the structure could potentially look like. So before we get started, let's go ahead and define our values here. So any two consecutive integers. So we're going to say let n and n plus 1 be be consecutive integers. So again, I don't have to use n and n plus 1. I could use n minus 1 and n, or I could use 2n plus 1. It's really up to you. I'm just trying to make the numbers as small as possible. Again, try to make things easy for yourself. It's already going to be stressful when you guys are looking at these types of questions. Okay, so we're going to let the sum of the squares of these two numbers. Okay, so we're going to have n squared, and we're going to have n plus 1 squared. And because we're looking at the sum of these, we're going to add these together. So this means that we're going to have n squared plus, and let's go ahead and distribute or expand this. We know that n plus 1 squared is n plus 1 times n plus 1. That gives me n squared plus n plus n plus 1, which is just n squared plus 2n plus 1. All right, so I'm going to go ahead, put this in here. So that's going to be n squared plus 2n plus 1. And then this will give us 2n squared plus 2n plus 1. And this is typically where most students will get stuck. Okay, so did anyone see our solution here based off of what I've written earlier up top? What do we need to do to get into that formatting that we see up near the top. So we're going to have to do something to our terms here. Can anyone see it? Have you spotted that last step? We're going to factorize, well, more like we're going to take out a GCF, because remember, you see, hopefully you guys see this portion here. We need a 2 times something, and then we're going to either add or subtract an odd number. This is going to be our odd number already, okay? That +1, we want that +1. But the key here is recognizing that because I want this 2 on the outside, I'm actually going to factorize a 2 or take out a GCF of 2 from just the first 2 terms. So this will give me, this will give me n squared plus n just from those 2, and then +1. So some people might choose to factorize out the n as well. That's perfectly fine. But all we need to do is just factor out that 2. Okay, do we understand why we did that? So we want this 2 on the outside, right? Because we know that our answer should be 2 times something, and then plus or minus an odd number, okay? So that's why we need to do that. We don't factorize the entire thing. We just have to show that our end result is some sort of even number, and then plus or minus an odd number, okay? So again, just to kind of summarize this portion here, we can see that we have an even number. So we have an even number. And then here we have, like I said, plus an odd is always going to be an odd number. Okay? Are you feeling okay about that one? I didn't get a lot of people responding. I'm not sure if you guys are just shy or if you weren't quite finished. How many of us found that a little bit tricky? Can I get a thumbs up in the comments if you found it tricky? Okay. Yeah, so that one was a little bit tricky. Okay, so maybe, I think this will be a good working level then. So I'll give you guys another, or we'll work through the second one then. And hopefully this will make a bit more sense once we work through this one. All right. So this one is saying that we want to be able to prove that the difference between the squares of any 2 consecutive integers is equal to the sum of these integers. Okay, so it's going to feel like kind of like Inception here, where we're going to do something with the numbers and show that they're equal to those numbers. Okay, so let's break this down into separate portions. So we're going to look at the difference between the squares of any 2 consecutive integers has to be equal to the sum of these integers. Okay, so there's a lot happening here, but we're going to make sure that we can kind of see exactly what it is we're working with. So this part in the yellow has to be equal to this part in the green, okay? So before we can even get started, let's go ahead and define our integers first, okay, before we can actually put this together. Let's do some black. So let's say that we're going to have let's go with let x and x plus 1 be 2 consecutive integers. Okay. So let's look at the green portion first. Oops, I accidentally messed that up. So we want something and something to be equal to the sum of these integers. So x plus 1. So this will be the sum of our integers. Okay, hopefully we can see that connection. So we need something to equal to 2x plus 1. Okay, and that's going to be at the very end. And now we're going to look at the portion that's highlighted in the yellow. So the squares of any two consecutive integers. So now if we're looking at the squares, x squared, x plus 1, these are the squares of those consecutive integers. Okay, so these are my squares. That's an awful arrow. So these are my squares of consecutive integers. Okay, so the squares of those consecutive integers. All right. So if we're looking at the difference, we're going to put the bigger number first, and we're going to subtract the smaller number, okay? So the bigger number is going to be the one where we have x plus 1 squared. So how we're going to set this up is that we're going to have x plus 1 squared minus the x squared here, okay? So this is the difference between the squares of any two consecutive integers, and that's what we want to see, okay? So this portion here, I'm actually just going to leave here at the bottom, okay? We'll leave it off on the side. So let's do this. Because we're trying to prove, basically, that this part in the yellow is equal to this part in the green, okay? I'm just going to leave it like this. So we can say that this is the sum of two consecutive integers. So that was the easy part. And now we're going to actually figure out, well, what is this equal to? So let's go ahead and expand this. X plus 1 times x plus 1 minus x squared. We know that this will be x squared plus x plus 1 minus x squared. We're going to cancel out the x squareds, and we're left with x plus x, which gives us 2x, and then plus 1. So we can see that these are the same, okay? So you can say, therefore, the difference between the squares of two consecutive integers is equal to the sum of those two integers. Okay, so that one looked a little bit more difficult, but it was actually, I think, in reality, a little bit easier. Okay, can I get a thumbs up if we understood kind of the thought process behind that? So again, maybe you might not quite get it from the start, but I think my goal tonight, especially with only a few more weeks before your exams, just to kind of walk you through that mindset of working through these types of problems, and hopefully, something will click when you guys are working through these. All right, I'm going to show you guys one more type of question that you might see. So it's slightly different than the ones that we've done. But again, it's nothing that you wouldn't be able to do, but I think it's just in terms of the language, it might scare you off a little bit, okay? So this last one here, and then we're gonna take a look at an exam question and then move on to some vector problems. So this one here, we are, again, looking at more or less the exact same thing, but because the language is a little bit different, it might throw you off a little bit. So it says, prove algebraically that the sums of the squares of any two consecutive even numbers is always 4 more than a multiple of 8. Okay, so a lot happening here. And especially that last portion, I think, is the part where I think a lot of you guys will struggle. So I'll give you guys a couple minutes to try to get started. I feel like some of you guys might get a little stuck. But again, I would advise that you try to figure out what your end goal is going to look like, okay? And start to work towards that by figuring out everything else before that end goal, okay? So even if you don't make it all the way to the end, if you're doing a 3-mark question like this one, you can at least maybe pick up 1 mark or 2 marks, even if you don't quite make it the whole way, So I'll give you guys a couple minutes to try this one out on your own. All right, so you got the 2n times n plus 2 plus 4, but you're not sure what to do next. Okay, so at some point you should have an 8 as your term on the outside. So I'm not sure what you might have done wrong there. I think you might have expanded your brackets incorrectly because you should have bigger numbers than that. And it doesn't matter, again, what numbers you start off with, as long as they're two consecutive even numbers. So we'll give everyone maybe about 30 more seconds. Yeah, I think you might have expanded incorrectly if you've only ended up with 2n as your greatest common factor on the outside, is what it looks like. Did you start with 2n and n plus 2? Or sorry, 2n plus 2? Okay. Yeah, you should end up with 8 as your GCF on the outside once you factorize. Okay, so let's break down this question. Again, looks scary just because of this part or this portion at the end. So Oscar, you were getting kind of close with that plus 4 at the end, so it's good that you recognize what that's going to look like. So it says prove algebraically that the sums of the squares of any two consecutive even numbers is always 4 more than a multiple of 8. So 4 more than a multiple of 8, what that's going to look like is we're going to have 8 times something plus 4 is what we're aiming to get, okay? So to be able to prove that, we're going to be working with the sums of the squares of any two consecutive even numbers, okay? So the first thing we're going to do is define what our consecutive even numbers are going to be. So we're going to say let 2n and 2n plus 2 be two consecutive even numbers. Okay. And then the squares, 2n squared and 2n plus 2 squared, are the squares of two consecutive even numbers. Okay. So because we're looking at the sums, now we're going to go 2n squared plus 2n plus 2 squared. So I'll give you guys a second there to write those down. And this just means that we're going to expand. So this gives me 4n squared plus 2n plus 2 times 2n plus 2. This means I'll have 4n squared plus 4n. 4n squared plus 4n plus 4n plus 4. So I'll have 4n squared plus, not 4n squared, I'll have 8n squared. 8n squared plus 8n plus 4. And hopefully at this point you can kind of see what's happening here. So we need to factor out an 8 so that 8 comes out in front. But we only do that with the first two terms. And then we have that plus 4 here at the end. So now I can say that we have a multiple of 8. Multiple of 8. And over here, we have 4 more. Okay? So we have a multiple of 8 and then 4 more. So the important part of being able to prove what you have is making sure that you write some sort of sentence or at least show what's happening in your proof. If you left it like this, I would wager that you'd probably end up losing 1 mark because you have to actually explain what we're looking at here. So just saying that you have a multiple of 8 here and then 4 more will be enough to get you the mark. If you've left it, like I said, like this without this explanation down here, you'd likely lose a mark according to the mark scheme. Okay. Why didn't I add the 2n and the 2n plus 2? So remember, I'm looking at the squares of those two numbers, right? So I have my two numbers, 2n and 2n plus 2. I have to square this one, and then I have to square this one, and then I'm adding the squares together. I'm not adding 2n, 2n plus 2 first and then squaring. So it's like saying the squares of 3 and 4. So that would be 3 squared and then 4 squared. I'm not doing 7 squared. Hopefully that makes sense. Okay. Okay, so maybe I'm going to quickly show you guys an example of an exam question from the AQA test. So, oops. So this is one from I think it was I want to say November 20. Which year was this one? November 2021, I believe. So November 2021. So this is 4 marks. So again, it's not, it's nothing too crazy. Now that you guys have actually done this, I'm not actually going to go through the entire entire question, but you guys can see that the structure is pretty much the same, right? You're going to have to prove that something is a square number, right? So at the very end of the day, we need to look for something squared. And we can see here that we want to start by expanding. So expand and simplify. Then what we're going to end up doing is we're going to have to factorize. And then we want to end up with something squared. Okay. Are you feeling okay about that question? So if you're curious, we will end up with, I believe it was x plus 6 squared at the very end. So if you want to try this on your own, because I do want to talk about vector proofs very quickly before we finish off for today. So the answer for this one ends up being x plus 6 squared. Okay. And this is worth 4 marks, right? So you get 1 mark for expanding. You get 1 mark for, actually, you know what? Let me show you the mark scheme for this. Let me just show you the mark scheme. And maybe what I'll do, you guys can just take a picture of the mark scheme and just put it aside so you can try this question on your own first before you check the answer. So it's going to look like this. Let me move down a little bit. So this is what the mark scheme is going to look like. So maybe I'll put that up here with the question. So you get 1 mark for expanding and then simplifying. Or actually 2 marks really, depending on which portion you look at. You get 1 mark for expanding the first set of brackets. Then you get another mark for actually putting everything together. You get a 3rd mark for fully simplifying, and you get your 4th mark for factorizing. So all in all, not too bad of a question, honestly. But I'm sure that looking at something like this is going to look quite scary if you haven't revised for it. But hopefully now you guys can find it a little bit easier. Any questions about algebraic proofs? Are you feeling much better about it, hopefully? All right, good stuff. So we're going to look at some vector proof problems. So these are the ones, again, it's kind of an extension of the vectors lesson from the other week. And I want to talk about a few of the things that you want to make sure you understand about vectors, okay? So vectors on their own are already pretty difficult, but we want to make sure we understand what's happening when we're asked to prove something. All right, so let's go ahead and look at this question here. So it says that ABCDEF is a regular hexagon with center O, and we're given this diagram here. So I'm going to give you guys a minute to quickly copy down this diagram. I'm not sure why those arrows look kind of a little bit weird. The arrows should actually be on top here. So this is what this should look like. The answer to the last question ends up being x plus 6 squared. Like this, x plus 6 squared. No problem. So I think what I'll do is I'll kind of walk you guys through this question, and then I'll give you another question that you can kind of try on your own time. I'll give you the answer to it, and we'll kind of end it off with that, because I think this is more of one of those types of units where you really just have to practice it, and hopefully I've given you guys the tools that are necessary just for you to go out there and practice again, using resources like Corbett Maths. Maths Genie, Dr. Frost, another fantastic resource. So lots and lots of practice out there for you guys. Okay, so I'll give you a second there. Go ahead and copy that down, and then we'll talk about what it's going to look like, or what your answer is going to look like. Let's give you about 30 more seconds. Copy that down. I'm actually going to shrink all of this so it's all on one screen for me. All right. So here's the walkthrough for this question. So again, I'm going to put myself in your shoes. You're looking at this on exam day, and you're thinking, I have no idea what to do. I have a shape. I have a whole bunch of arrows. I don't know what's happening. So I'm going to direct your attention to what we're actually being asked to do here. We want to be able to prove that E, M, and X are on the same straight line. Okay. And before we kind of figure out what's happening here, X is the point on AB extended. Okay. So we're going to extend this line AB and have some point X such that A to B and B to X is in the ratio of 3 to 2. Okay. So B to X is going to be slightly shorter than A to B. All right. So basically, we're saying that if I drew a straight line, and is this the line? There you go. So let's go ahead. Let's draw that line here. That was close. I'm going to get rid of this actually. So let's get rid of this, and let's call this X. Let's make this a little bit shorter, just so if I can actually grab that point. I'm just gonna use my mouse here. Come on. And grab this line. Let's make it a little bit shorter. Kind of like this. Good enough. Maybe a bit shorter. All right. So we're going to call this X. All right. So that's the first thing that we need to do. And we can see that this is in the ratio of 3 to 2. Okay. So we're going to leave that alone for the time being. We're going to look at what we're actually being asked to prove. Prove that E, M, and X are on the same straight line. Okay. So can anyone tell me what you think that might mean, or how we might go about solving it? Because that's really the key to understanding this problem. Because otherwise you're going to sit there, you're going to figure out a whole bunch of things, and you'll have no idea what's actually happening. what do we need to do? Any guesses? We are going to have to find A to B at some point. But at the very end, what should our answer look like? Because that's going to be really key in helping us figure out, well, what are the steps we need to take in order to get there? So E to M to X. That's what we're trying to find, or to prove rather that they're on the same line. Okay, so we need a number outside a bracket. And then what do we need to do? What do we need to compare that with? It's actually a really good start. Number outside a bracket. So maybe what I'll do is I'll draw a line here and just to give us a visual of what's happening. So you want to show that E to M to X. Okay, and I'll shuffle everything over just so it lines up a little bit better. So you want to show that E to M to X. Maybe I'll do this in like a blue or something. You're going to show that E to M to X are on the same line. So Oscar, you are definitely on the right track, saying that we need a number outside the bracket. So pretty much what this question is asking us is we want to show that E to M. So if this is true, E to M and M to X they will have vectors in the form of K with something on the inside. And K is just going to be some sort of scalar multiple or a scalar constant, okay? So it's just going to be some sort of number. 2 could be 1/2, okay? So that's just going to be some sort of number on the outside times a vector. That's not the only part though. And they both have to pass through point M. All right, so that's what we're looking for when we want to be able to prove that these 3 points are on the same line, okay? Hopefully that makes sense. Oh, sorry, I'm getting a little ahead of myself here. This should say E to X rather. My apologies. E to X, and it's going to pass through point E rather. I was looking at this and said, that sounds a little weird. So E to M and E to X are going to both pass through E, and they're going to have your vector in this format here. So let's go ahead and actually solve this question. So Oscar, you suggest that we need to find AB, which is correct. We're going to find AB, but that's actually going to be our second step because I want to figure out what BX is first, just so we can understand why we need to find AB. Okay, so we're going to go and define BX. So vector BX is equal to 2/3 of vector or of line rather A to B. Okay, so you've got vector AB. So 2/3 of that is equal to vector BX. And that comes from this ratio here. So 2/3 AB is what gives us BX. Okay. And now what we can do is see that we need to find out what AB actually is. So what is A to B? A to B, we're going to look for an alternative pathing. Okay, so what I like to do is draw what vectors I would add. So I'd have this vector coming this way, so it's going to be negative A, and then we're going to add B. So negative A plus B gives me vector AB. Okay. So as a result, I can figure out what vector Bx is. So this means that Bx, so therefore Bx is equal to 2/3 of negative A, and maybe I'll do this in green just to color coordinate. So 2/3 of negative A plus B. So 2/3 of negative A plus B. Okay. Can anyone tell me what we need to find next? Any guesses what we might need to find next? What's the next thing that we're going to have to find? B to M. Perfect. So we need to find B to M. Okay, we need to find B to M because at some point we need to find out what E to M is. And the only way to figure that out is if we have B to M. Okay, so vector BM, B to M, and we're going to use this point right here, or this statement, that M is the midpoint of BC, along with something else. What can we do? It's negative 1/2 A. Excellent. So Stan, how did we figure out that it was negative 1/2 A? Where does that come from? How do we justify where that came from? BC is the same as negative A. Yes. Okay. And again, that's because we're looking at a regular hexagon. Okay. So because we're looking at this regular hexagon here, okay, we can see that BC is going to be the same thing as vector A to O. Okay. So it's going to be negative 1/2 A, right? So negative 1/2 A, because we know that this whole portion here, so this whole thing is negative A, but because M is the midpoint of that, we're just going to take half of that negative A. All right. Perfect. What is our next step going to be then? What can we do now that we have all this information? Because we've gotten pretty much all the information that we need. What can we do? What were the two things that we wanted to find? We wanted to find E to M, and we also wanted to find E to X. So I'm going to go and shrink this down a little bit. So let's go ahead. Let's shrink this. Why is this not shrinking? Apparently I can't shake this. Let's just group this. So I'm going to move this, group it, and then we're going to shift it over here. And we're going to start off by defining what E to M is. So vector E to M, what can we do there? There's a couple things. E to M. How can I find E to M? So E to B plus B to M, perfect, okay? So we know E to M is the same thing as E to B plus B to M. So I'm actually gonna get rid of this. I'm gonna get rid of this here because this is a little bit distracting. We don't actually need that, okay? So E to B, so I'm gonna go ahead and actually just redraw this line here. So E to B, so we know that this is also going to be B. So E to B is the same thing as 2B. And we just found out that B to M, oops, forgot my vector arrows. So we have 2B plus BM, and we said that was plus a negative 1/2a, or I can just go straight ahead and say 2b minus 1/2a, and that gives me e to m. And then now I want to find out what e to x is. So what is e to x? Well, e to x is the same thing again as what? E to b, vector eb, plus vector bx, which are the ones that we've already found. So this gives me 2b, and then vector bx was 2/3 of negative a plus b. And again, we're going to simplify a little bit. So 2b plus, oh, not plus, we're going to have a minus there. It's going to be minus 2/3 a, and then plus 2/3 b. And we can simplify this. We can change this 2b into a common denominator with the 2/3 b. So that's going to be, what is that, 6/3 b plus 2/3 b. And I'm just going to move that 2/3 a to the end here. So this gives me 8/3 b minus 2/3 a. All right. So what I'm actually going to do is I'm going to move all of this down here so that we have a little bit of space to think, and I actually want to be able to compare these two. I just kept these up here just so we can work with the actual diagram itself. I'm going to move these down here. And remember, our goal is to be able to factor something out and have the same thing inside the brackets. That's our end goal. Okay, so you can see here that we're going to have b and a somewhere. Hopefully you guys can see that. Okay, that b and a is what we want, but we want to be able to factor something out. So let's figure out what we could factor out. So typically we want to try to get rid of any fractions. Okay, so we're going to get rid of any fractions. And in order to do that, we're going to factor them out. Okay, so let's look at e to m first. So e to m, we're going to go ahead and factor out a 1/2. So 1/2 comes out, and 1/2 times something has to give me 2b. We can think of this as 2 divided by a half, right? 2 divided by a half, I'll do that up here. 2, we can pretend 2 over 1, divided by 1/2 is the same thing as 2 over 1 times the reciprocal of 1/2, which is just 4. So that gives me 4b minus a. So I have 4b minus a here. And now I want to do the same thing over here. Okay, and we'll notice this one's going to be a little bit trickier because we're going to be able to factor something out from the top as well as something out of the bottom. Okay, so over here, I can factor out a 3 in the denominator. So I'm going to factor out a 3. But on top, we notice that we can factor out a 2. So I'm going to factor out that 2/3. I'm going to be left with 4b. So again, if we check this, or we check our answer, 2/3 times 4 gives me 8/3. And now I factored out that 2/3 from here. This will give me minus a. All right. So we definitely have, right, 4b minus a. And they both pass through e. So we can go ahead and say, since e vector em, since vector em and vector ex are multiples of 4b minus a, and both pass through e, em, and x are on the same, I think it said same straight line, same straight line. Okay, so since vectors em and ex are multiples of 4b minus a, and they both pass through E, M, and X are on the same straight line. So I'm going to leave you with two other examples that are pretty similar, or they're pretty much exactly the same thing, but just to get you guys to think about the language that's being used and how to solve it. I'm going to put them on the screen so you can take a quick picture here. So I'll put one on here, and I'll put the second one on here as well. So let's do this one first. So let's do this one. I'll make it a little bit smaller. And I'll put the second one on the same screen as well. So I'll do this one here. And let's do this one. And then, yeah, and then that kind of brings us to the end of today. Bit shorter than usual, but again, I think this is one of those topics where, I can only talk for so long and you guys actually just have to go and just do it. Because otherwise I can talk your face off. But it's really about you guys applying the same kind of work. Okay, so you can see these two questions are very similar to the one that we did, using that same language of being on the same straight line. So you want to identify what it is that you're trying to find out. Okay, identifying the vectors that you need to use to get there. Okay, and apply that kind of formulation. So typically, proofs for vectors are going to look something like this style of question. Yeah, so that's pretty much it for today. Thank you guys for joining me. I hope you guys have learned something new and you feel a lot more confident about proofs moving into the next couple of weeks. Thank you guys so much for coming out, and I'll see you guys later. Take care. Have a good night. See you later, guys.